Welcome to the 10th session of research discussion on graphs and groups. May I request Professor Tamil Selvam to introduce the speaker.
Good evening to one
Good
and all.
evening to one.
Of course, it is happy to introduce the speaker of the today. Really, I am thankful to Professor Vijay Kumar and Barna. Today's speaker is Professor Alireza Abdollahi. He is currently professor from Department of Mathematics, University of Isfahan, Iran. Of course, he had his master degree as well as doctorate from the same university during the year 2000. And subsequently, he had another PhD from University of de France, CMI, France. Of course, his specializations are combinatorial conditions on finite and infinite subsets of groups and rings. And of course, angel elements in groups, integral Kelly graphs, graphs from groups. Apart from his research positions, he had a very good record of several administrative positions, of which the head the Center for Excellence in Mathematics, and of course he was appointed as the head of the center by the Ministry of Science and Education of the government of Iran. Due to his credibility in research, he is editor-in-chief for two internationally reputed journals. One is International Journal of Group Theory, and another one is Transactions on Combinatorics. Both are devoted to quality publications. Of course, he has published around 112 papers in SCI journals and leading journals in mathematics, especially algebra and graph theory. He has got many awards to his credit, of which I just mentioned one. He is awarded Young Mathematician Prize by Institute for Studies in Theoretical Physics and Mathematics and various others. Of course, he is going to talk on graphs defined on groups via nilpotency conditions. On behalf of the organizing team, I welcome Professor Alireza Abdollahi. Please start.
Thank you very much for your kind introduction, and thank you very much for inviting me to talk in this series of conferences, seminars. Okay, thanks again for your kind introduction, and also thank you very much for inviting me in this series of seminars. As it is said, I will take on graphs defined by groups via nilpotency conditions. I would like to state some results, some non-result mostly, and maybe some question for further study of graphs defined by groups. Okay, let me start with a noun definition. So we have a class of groups called P, and we denote by P of G the graph, whose vertices, as usual, is the set of elements of the group, and the set of edges are this pair of two subsets with two elements, which are X and Y, are not in the class, is not in the class P. This means that the class, the subgroup generated by X and Y. So, for example, what I want to take here instead of P is the class of nilpotent groups denoted by N and K, and I drop infinity also when it is nilpotent. When K is infinity, the class of nilpotent groups of nilpotency class at most K and the class of cyclic groups when we take k is equal to 0. So nk is, I mean by nk is n infinity is the same as the n, and n and this, for example, 2 is the class of nilpotent group of class 2, and n and this 1 n sub 1 is the class of the usual class of abelian groups. So the class ng, it means that n infinity g, the class we call the graph of ng is the non-nilpotent graph of g. Again, to clarify, ng is a graph whose vertices of the elements of G and two elements are joined by an edge if they do not generate an nilpotent subgroup of G. And if K is an integer, we call N and this Kj the non-nilpotent K graph of G, if we need to call it. And so this graph is, for example, is has been studied by many people. For the k is equal to 1, this is the non-nilpotent 1 graph of a group G, is the complement of the commuting graph of G. That is the graph that the set of elements are the set of vertices are the elements of G, and two vertices are joined by an edge if they do not commute or they do not generate an abelian subgroup. And the case 0, the non-nilpotent 0 graph, is nothing except of the complement of the enhanced power graph. So this is called the complement of the enhanced power graph of G is denoted by N0G. So these are examples. So my main question, what is the main question here? Main question, in my opinion, of course, is its origin in the question by Paul Erdős. This is a review in mathematical reviews by Paul Erdős himself of the paper of Bernhard Neumann. So what is, in my opinion, the main question is that assume that PG contains no infinite complete graph. Is it then true that there is a positive integer n such that PG contains no complete subgraph Kn? So we know that all the cliques of a graph are finite. But the question is that is there a bound on the size of these cliques? So the question is something like that. And actually, Paul Erdős proposes such question for when he has taken P the class of abelian groups. As it is the words of the Paul Erdős is here, let G be a group, join two elements of G by an edge if and only if they do not commute. And let gamma be the graph which is associated in this way to G. The reviewer asked the following question: assume that gamma contains no infinite complete graph, is it then true that there is an n depending on G, so that gamma contains no Kn, complete graph of n vertices? And the author, Bernhard Neumann, proves that this conjecture, in fact, it is shown that this class of groups is exactly the class of groups whose center are finite index or finite index in the group. So also it's stated that the Mackenzie and Faber has also obtained this result, but according to McZinet, the result published 2 years after it is published in 76, the paper of Neumann, but the paper of Mackenzie and Faber published, I think, in 78. Okay. So, I would like to. So, in what we see in the sequel is that I would like to replace the class P with other class of groups. Of course, class which are interesting or simple in some sense, and I would like to see what happened. Is it possible to find similar similar results as a BH Neumann, or is it possible to say to answer yes or no to this question? So actually,
sorry, I have a question. I have
yes,
a question.
Please, please.
Is the answer known to this problem? What is the answer to this? Is it been settled?
For
the non-commuting, for the non-commuting
yes,
graph.
Yes, of course, it is known. It is known because let me go further in next slide. Actually, okay, if P is equal to N1, the answer is positive. So for such a group G, the index of the center in G is finite, and this index can serve as the requested n in the question. So we can find a universal bound on the cliques of the non-commuting graph of a group if we know that all the cliques of the graph are finite.
I see. Okay.
Okay. So actually, this is more than we expected wanted. We know that this structure is very restricted. This is ZG. The center of G has a finite index in G. So okay, we know that. So let me say something. Okay, in about the class of cyclic group, or N0, P is equal to N0. N0 means that the class of cyclic groups means we have a complement of a enhanced power graph. So again, we know that the answer of a Erdős-like question is again positive. Actually, we know further. We know more than we need. Actually, we know that this index, the cyclikizer of G, has a finite is a finite index in the G. What is the cyclikizer? We denoted by this one. It is defined by some students, I think that bachelor students, undergraduate students in Rose-Hulman Institute, I think, if I am not wrong. But this is very interesting. Cyclikizer of G is the set of elements in G, like C, such that the subgroup generated by any element of any element X of G is cyclic. This is the class of cyclic groups for all X. So actually, this is the set of isolated vertices in the enhanced power graph. Cycle sec of G is the set of isolated vertices of the enhanced power graph. And again, this index can serve as the requested n in the question. In the question, I say question, I mean this red question. Assume that PG contains no infinite complex graph. Is it then true that there is a positive integer n such that PG contains no complete subgraph Kn? So again, we have find another class of groups. Cyclic groups means that Muhammad Hassan Abadi. And about the proof, I can say that it is easily seen that by the result of Neumann, the center of such groups is a finite index. So what remains is proof that the index of the cyclic Isor in the center of G is finite. So actually, you can think about the question in Abelian case. Note that the cyclic Isor always in the center of G, is the subgroup of the center. It is obvious that it is obvious. It's interesting to note. It is interesting to note that this cyclic Isor is a subgroup. Actually, is a subgroup of any group. Okay, so we have another class of groups that have a complete, the similar result as a Neumann. So actually, the first attempt to generalize the question, or maybe better answer questions similar to polar douche have been done by Lennox and Weigel in 81. They have considered Lennox and Weigel consider the question for the class of nilpotent groups, for the class of coherent groups, and for the class of polycyclic groups. But under the further condition that the group must be itself finite generated and solvable. So they have studied actually the graph NG for groups which are finitely generated and solvable, and also the class P when it is polycyclic group. By polycyclic group, you know that a group having a series of subnormal subgroups whose factors are cyclic.
And what is ZK? ZK?
Okay. ZK is the K+1 center of the group. Is the K+1 because the first one is Z0 and Z1 is a center of G, and etc. Z2 is an upper central series of G.
Oh, the upper central. Okay.
Yeah, the upper central series of G, but it is a K+1 member of the series. Okay. So, okay, they have found actually that the group is finite by nilpotent. What is finite by nilpotent means that the group has a finite normal subgroup whose coefficient is nilpotent. But under the condition that we have a finitely generated, one can see that the index of zk for some k is finite. And it is enough for us to see that this index serves as a this index, the index of this subgroup serves as the n we need in our question. So the class of, actually for the class of polycyclic group, they have proved more. They prove that if G is a finitely generated solvable group in which every infinite subset contains two distinct elements generating a polycyclic group, then it is itself polycyclic group. So actually in this case we have no the graph has no edges in the case if we add the condition that have no infinite clique. And class of coherent groups is the class of groups in which every finitely generated subgroup is finitely presented. So by coherent groups, but maybe this class is seems very complicated, but they have used the result of Gross or someone else, I do not remember correctly, that in a polycyclic case, in a finitely generated solvable groups, a group is fine. Actually this is equivalent to the condition to the polycyclic of some kind of subgroups. So anyway, but this class is somehow bizarre. Anyway, so we have also, but what I want to stress here, we have positive answer to Erdős-like question under the further condition finitely generated plus solvability. Without these two, we cannot prove that actually this conclusion are false, and it is not because of the we know that there are groups they are groups which are not nilpotent, but but every two generator subgroup is nilpotent. So because of these groups, we cannot drop the condition finitely generated and solvability. Okay, and they have left a question about the same question for replacing n by super solvability. And I think that, okay, John Gross from Melbourne University answered positively that again actually what Gross proved that if G is a finitely generated solvable groups in which every infinite subset contains two elements generating a super solvable subgroup, then G is finite by super solvable. And this shows that we have a universal upper bound on the size of the cliques of a graph when we consider instead of P the class of super solvable groups. Okay. I have not find the picture of a photo of John Gross, unfortunately. Anyway, now another class that we know, of course, with the further condition that G is again finitely generated and solvable groups, is due to Costantino Delizia. he has proved that the finitely generated solvable groups in which the graph N2G means that the graph whose vertices of the elements of the group and the edges are pair of elements generating a subgroup which is not nilpotent of class at most 2. So he has proved that again we have a positive answer. Actually, he has proved more. He has proved that the second center of the group has a finite index in the group. But this implies that we have a universal upper bound on the size of the cliques of our graph. And we have answer again in the under the condition of finitely generated unsolvability that if we take nk means that the class of nilpotent groups of nilpotency class at most k, that again the answer is we have a positive answer to a Erdős-like question. So this is done with Tyree. Okay. So we have again the positive result. But again, I should say that we don't know if we drop the condition finitely generated unsolvability. And now one can change the class of finitely generated unsolvability with somehow difficult class, I can say, residually finite. And this is done by Costantino Delisi again, that we have a positive answer that we have a universal bond on the size of the cliques. When we assume that group is finitely generated and residually finite, by residually finite means that the intersection of all normal subgroups which are of finite index in the group is finite. So with this condition, one can prove the Costantino Delisi has proved that again. Of course, he has proved more. He has proved that the second center again of the group has a finite index in the group, but it implies that we have a universal bond on the cliques of the group. And okay, we have defined with Zarrin, Muhammad Zarrin, and somehow systematically studied the non-nilpotent graph. If G is not weakly nilpotent, by weakly nilpotent, groups the groups every two generator subgroup is nilpotent. Note that it is not true that if every two generator subgroup in general, not necessarily for finite groups, if a group every two generator subgroup is nilpotent, it is not true that the group is nilpotent. Even it is not true that the group is locally nilpotent. Locally nilpotent means that every finitely generated subgroup is nilpotent. But it is true for finite groups. In fact, in finite, a group is nilpotent. A finite group is nilpotent if and only if every two generator subgroup is nilpotent. And in finite case, but in general, we have a study in general. If G is not weakly nilpotent, then diameter of the non-nilpotent graph is at least 2. This does not imply that the NG is connected. Actually, I am using this definition of diameter that the maximum of the diameter of the component of the graph, because sometimes some authors define that diameter is infinity when the graph is disconnected, but we define the diameter is a maximum of the diameter of the component of the graph. So in this case, we know that the diameter is at least 2, and if G is not weakly, if G is weakly nilpotent, then we have no edges, of course, for the NG. So it is not interesting. So okay, and the girth of the graph is exactly 3 in the case of the, of course, if G is not weakly nilpotent. Okay, this is a and also we have proved that we have find a nilpotency criteria by NG that a group is a finite group, not an arbitrary group, is nilpotent if and only if the set of vertex degrees of NG has at most 2 elements, means 1 or 2 elements. This is done by Zarin, and okay, we have also proved that in that paper that for finite non-nilpotent groups, not that the nilpotent, as I said, the finite group is nilpotent if and only if it is weakly nilpotent. Weakly nilpotent means that every 2 generator subgroup is nilpotent. So when we assume that, so we are assuming that in the finite case, we assume that the group is non-nilpotent. Then the induced subgraph of NG on the set of non-isolated vertices is a connected graph. Means that consider the NG and then delete all isolated vertices. Don't consider the isolated vertices. And so this graph is connected, and we have proved with Zarin that the diameter is at most 6. But we felt that the 6 is not a correct bound for the diameter of this not for NG, but for the induced subgraph of NG, which is considered on the 9 isolated vertices. And okay, we have asked what is the best possible bond on the diameter, and Andrea, Kini, and Daniel and Nemi proved that the diameter of the non-nilpotent graph of a finite group is 3 actually, and 3 is the best possible bond. So we know that this graph NG without the isolated vertices is connected, and its diameter is at most 3. And we know also some results about the click number of the graph. This can be affected the group if, for example, if the omega of NG means that the click number of the graph means that the largest click or largest complete subgraph of the graph NG is if it is less than or equal to 3, then the group is nilpotent. Means that we have no click must be for non-nilpotent groups, then click must be more than 4. And this one we have solvability if we know that the click is less than 20. This is proved by Girard and Dimioni in this paper. Actually, I have a picture of Gerard, but I couldn't find it. I have some photo with him, of course, because he was my supervisor in France. But anyway, okay, yeah, and so other questions. So I do not want to say that this is the only question we must consider in such graphs, but other questions coming by Lucchini and Nemi. It's a very recent paper. You can find it in archive. In the following paper by Lucchini and Nemi. Nemi he was a master student, I think. You can find his master thesis, I think less than 40 pages in there, but it contains nice results. They consider the graph PG when the class P is considered to be a formation. What is a formation? Is a class of groups, again, which is closed undertaking coefficients and finite subdirect products. For example, abelian class of abelian groups, class of solvable groups, class of nilpotent groups are all formation. And they have. I do not want to share with the result detail to say about the details of the result, but they have actually in this paper considered these two questions for a finite group at G and a formation P, of course, with some further conditions, assuming that P is hereditary, means that every subgroup of a group in this formation against in this subformation. They have considered these two questions. Is the set of isolated vertices of PG a subgroup of G? For example, in complement of the enhanced power graph, the isolated vertices are is the cyclic-izer of G. It is a subgroup, for example. So for the class, if P take P, the class of cyclic groups, we have a positive answer. And also for the, if we take P, for example, the class of abelian groups, means consider the non-commuting graph of a group or complement of the commuting graph. So we have the center of G. So this is again a subgroups. So they have studied a bit, I think, with some saturated formation and also hereditary and some condition. They have find some nice result in generalizing. And again, the question about the when we consider the graph by and deleting the isolated vertices, asking that this induced subgraph is connected or not. This is important. This is nice question. So you can see this paper to that if you are interested in. And I think that I am finishing my talk, but this is I think that the last paper, maybe two of the last paper, one of the I don't know, of the Bernhard Neumann recorded in MathSciNet. According to MathSciNet, it is, I think that after this paper, ensuring commutativity of finite groups, he has a paper I don't know about the some personal collections of SciShow, something like that by Neumann. Anyway, in this very short paper, 2 pages, ensuring commutativity of finite groups. Let me see that if I have the paper, show you here. Let me see. No, I didn't have. I have put in the. Let me see. Okay. No. Anyway, let me try to find it for you because we have time, I think. And I want to show it. Okay. No, this is not the, this is another paper. Ensuring anyway, this is a 2 pages paper I can find in my laptop. It's proposed by the following question is proposed to a study for a finite group G and a formation. Oh, sorry, this is not for this slide. And this is ask. This one is exactly the question. Let G be a group such that N1G. N1G means the non-commuting graph of the group. N1 is the class of group nilpotent groups of nilpotency class at most 1 means that abelian groups. Assuming that G is a group, G is a finite group, of course, here. Anyway, arbitrary group, such that has no complete bipartite K and M for some positive integers M and N. So under what conditions on M and N is the group abelian? Of course, let me say that Bernhard Neumann didn't speak of a graph, of a non-commuting graph. The condition he has considered can be translated to this. Condition he has proposed is as follows. Consider the group has this condition. Every 2 subset X and Y of G, X contains n elements, Y contains m elements. You can find an element in the one subset and another element in another subset commuting. So this means that you have in this graph you have no complete bipartite graph. So if you find the paper of Neumann, you don't see any word of graph, but it is a translation.
Sorry, so for m equals 1 and n equals 1, clearly it works. So you want to make m and n large. Is that the problem?
Yeah. Okay. Of course. So the question is that under what condition on M and N the group abelian? We have a partial answer to this question. It's a very general question, of course. We proved that the order of such non-abelian group, such a non-abelian group, if there exists a non-abelian group, then we can bound the order of group by an exponential function in m plus n. So if if we have if the order of a group is larger than this function, then you can say that the group is abelian. And I think that now I'm finished. And let me say about that okay, we have minutes, I think. Brace has shown that the same result as ours when we replace abelian by supersolvability, or even more for some formations, and he has find some results. So let me, I think that I am finished now. It is okay. So thank you, I finished now.
The forum is now open for discussions. Comments and questions are most welcome.
It's the entire the theme seems to be very reminiscent of the compactness principle of, for example, first order logic or propositional logic. Like, if you don't have an infinite object, then you can bound this. You can't have infinitely many finite objects satisfying some property. So is it possible to formulate these as a kind of compactness principle, or at least some of these results?
Yeah, nice point you have said, but I don't know. I have no idea about that. Even I said that, for example, for the class of nilpotent of class at most 2, for example, we don't know if it is true. Of course, under the condition of finitely generated and solvability, as I said, we have now that we have a, but I don't know. Maybe as you saw the proof of Bernhard Neumann of polar Bush question, he has used the Ramsey theorem, infinite Ramsey theorem.
Oh, okay.
I don't know if it is possible. It is very difficult for me that even for the class of, for example, after the abelianness, it is a simple class, and the proof of Neumann is very tricky, and one must consider a class between abelian and the nilpotent of class 2, in my opinion. But we don't know about positive answer.
May I now request Dr. Jasmine to propose the vote of thanks?
Excuse me. It's my pleasure to extend profound gratitude to Professor Alireza Abdollahi, University of Isfahan, Iran, who was talking about graphs whose vertex set is a graph is a group G, and two distinct elements X and Y are adjacent if the subgroup generated by X and Y is not in the class P of groups. Thank you very much, sir, for your valuable observations and clarifications, which led us to be equipped with more knowledge in the area of graphs and groups. Once again, I am thanking you on behalf of the organizers and participants. Let me utilize this opportunity to thank the CUSAT team, especially Dr. Ambad Vijayakumar sir and Aparna ma'am, for these valuable discussions. Thank you all. Thank you very much.
Okay, before we disperse, am I audible?
Yes, sir. Please go ahead.
Yeah, the next week, 9th is going to be very significant and crucial, because we had already sent a mail asking for proposals to discuss on 9th by the participants. So the success of the program very much depends on that day, and we will decide about the continuation of this project only on that particular day. So please come forward, especially the youngsters. We have received 2 proposals, but I expect more from younger group, so that the purpose of this research discussion is fulfilled. So please spend the next 2-3 days to think about the various discussions that took place in this forum, and we come with some proposals latest by 3rd June. Okay, so that we can allot the timings for various speakers. So thank you very much for joining.